class. Okay, so we're going to talk about something called electric potential. And so, we kind of started out by talking about something very tangible, which are electric forces. If you have charged objects, they exert force on each other. Those are observable things and we can measure them. Well, we found, forces are interactions between two particles. And so we kind of abstracted from that this idea of the electric field. And an electric field is a property of a single particle. So if we have a charge, that creates this electric field around it. And then if we place let's just look at this point P. Now, there is an electric field at point P, even if this is the only charge around. We can talk about an electric field at that point P, and then if we place another charge here, now we say that this electric field that was created by this first charge is going to exert a force on that second charge. And so it's very useful to have this idea where we can talk about just properties of a single charge. And then we talked about energy, where again we started out by talking about the interaction between two particles. And like we had, say, Q1 and Q2, and there's energy. We calculate the work by moving one particle around in the presence of another. And so energy is a property of a collection of particles. But we want to do the same thing. So we've got forces and energy. And from forces, we kind of abstracted this idea of an electric field. And we want to do the same for energy. We want to define something. We're going to call this potential. Might not be the best name because potential, you think potential energy, but no, we're talking about just potential itself. It is not energy. So despite what the name might sound like, potential is not energy. But we're kind of going, the connection between forces and energy is the same as a connection between fields and potential. So the idea is we want to kind of define a property, the electric potential of a single charge. And so we're going to do this by, say we have a charge here, Q1. And if we place another, we call this a test charge, Q0. And so we know that there's a potential energy between them. Let's say they're separated by a distance r. Then the potential energy let's just call this Q and Q0. So the potential energy of interaction between these two particles is KE Q0 over R. And we're going to define the electric potential as the electric potential energy divided by this test particle, this test charge. And so doing that allows us, because let's say we place a charge of 1 coulomb here, then the potential energy would be, Ke times Q times a coulomb divided by R. If we place a charge of 2 coulombs here, then, the electric potential energy would be multiplied by a factor of 2. But then we're going to divide by this extra 2 here. And so the electric potential doesn't depend on this charge at all. We can interpret that we can define it to be just a property of Q itself. So the potential due to a point charge. So we use V for potential. And we say it's KEQ over R. That's just follows directly from the definition of how we define potential. And we use the letter V for this because the units for potential are volts. So think that's again the terms are very confusing. We have potential and potential energy, but they're very different things. So potential energy is measured in joules, and potential is measured in volts. And so we can see from this equation that a joule is equal to a coulomb times a volt. So let's write that down. Again, this is on the equation sheet. One of those unit conversions, very useful one. And this idea of a potential is extremely useful. So we can talk about the potential due to a single charge. We can also talk about the potential for a collection of charges. So let's say that we have, say, Q1, Q2, and Q3. And let's say we have a point P right here. Let's call that R1, R2, and R3. Then the potential at P would be KEQ1 over R1 plus KEQ2 over R2 plus KEQ3 over R3. So again, like every charge contributes this KEQ over R to the potential at any point. And this is an extremely useful concept, electric potential. Again, just like electric fields, are kind of more useful than electric forces. Kind of grasping this idea of a field from something more tangible like forces. Again, potentials have that same relation. And we're going to see later that there's a connection between the electric field and the electric potential. We'll deal with that in a later video, though. Now, so basically the electric potential for any number of charges can be calculated then. We have this formula for a point charge, and if we have a lot of point charges, we can just add it all up. And we can easily abstract this idea to a continuous charge distribution. But before we do that, I want to let's get rid of this picture. Let's get rid of everything here. Let's say we have a particle, or let's just say we have 2 points, A and B. And we want to talk about the difference in potential between these 2 points. Let's say we go from A to B. So VB minus VA we've got we have to imagine that there's let's just say there's one charge to make things simple. All right, now let's say that this charge, let's call this Q1. Now let's say we actually place a charge Q2 and have it move from A to B. And so the difference in potential energy let's write that down. We have KE Q1, Q2. Let's see. Yeah, we're going, let's say R is the distance from Q1. So that would be like RB minus KE Q1, Q2 over RA. So again, these RA, I wrote that one wrong. That RA is the R's are distances from charge 1. And we can factor a Q2 out of this. And we can see that UB minus UA is Q2 times VB minus VA. And so we get this, we can write this more compactly. In general, delta U is equal to Q delta V. So the change in potential energy, like if a charge Q moves through a potential difference delta V, then the change in potential energy is just Q times delta V. And that is a very important equation right there. I want to actually look at an example of that, but so we've got two things to do still. I want to talk about how we can, we've talked about how we can have find the electric potential due to any number of charges. So we have this formula for each charge, and if we have a finite number of charges, we can add them up. But there's also the idea of a continuous charge distribution. So I want to do an example of that, how we can just abstract that formula to continuous charge distribution. And also, I want to do an example involving that delta U equals Q delta V, like why that's such a useful concept. So first, let's look at a continuous charge distribution. And yeah, let's say we have a disk. So with a uniform charge distribution, say this is like our z-axis. Hardest part is going to be actually drawing this. So this disk is in the xy plane, and that's the z-axis. So again, it's hard to draw, but the disk is perpendicular. Disk is a radius r, and it has a uniform charge density sigma. So let's say we want to know the potential at some point P on the z-axis. So let's draw a thin shell, like a ring with a radius r and a thickness dr. So that's an infinitesimally thin ring. And so the charge on that ring, we'll call that dq. That's just the density times the area. And the area of this ring would be 2 pi r dr. Now, that wouldn't be true for a ring in general, because r changes as you go from like the inner radius to the outer radius. However, if it's an infinitesimally thin ring, you can just unfold it into a rectangle, and so this 2 pi r would just be the circumference, and then dr is the thickness of the rectangle. And so, again, that only applies for an infinitesimally thin ring. If you had a finite thickness, you'd have to integrate from the inner radius to the outer radius. And that's what we're going to do to get this disk. We'll consider just a collection of rings, starting at, thin one, and then just each one has a thickness dr. We build it up over the entire disk. So dq is, let's just do this. We have 2 pi sigma r dr. So that's the amount of charge contained in this ring. Now, actually, yeah, I've got to think about the notation here, because in this formula, let's keep this r. So in the formula we have kq over r, but let's just keep in mind r is the radius of this thin ring, and so let's call the radius the distance from the charge to the point. We'll have to give that a different name. Let's call that capital R. Now, in doing this integral, we're integrating over an area. And so, really we should consider a little element of dq, and then integrate around the ring, and then integrate the rings across the entire disk. However, we don't need to do that in this case, because every point on this ring is the same distance from point P. And, we're talking about scalars here, so the only thing that matters is the distance. And so we can say that the potential, let's call that dV, the potential due to this ring, then that would be Ke dq over capital R. So like this is, r is, lowercase r is the radius of the ring. Capital R is the distance from the ring to our point P, and let's call that Z. Okay, so now let's kind of put this together. We have 2 pi, and we have, let's do 2 pi Ke sigma r dr over capital R. Now, capital R, we have r squared. Capital R squared is little r squared plus z squared, where z is a constant. And so we can say r, little r is big R squared. Now let's just take the square root. Big R is little r squared plus z squared, the square root of that. And so let's replace that. Because, this is the potential due to this ring, and to get the potential of the entire disk, we're just going to integrate, over this radius r. And so we want to get all our variables in terms of, this integration variable. And so now that we've set this up, the potential due to the entire disk is, we'll take out our constants. 2 pi Ke, we can write it that way, but remember Ke is 1 over 4 pi epsilon naught. So 2 pi Ke would be 1 over 2 epsilon naught. We could do that. So 2 pi Ke is 1 over 2 epsilon naught. Let's do that. And either way is fine. So we've got this 2 pi Ke sigma, those are constants. And then we have the integral from 0. I'm having trouble with variables here because we use r for everything. Let's say the radius of the disk is a. So we'd integrate from 0 to a, r dr over the square root of r squared plus z squared. So we've set this up. Now it's just a matter of actually doing the integral. So again, let's kind of go back to the beginning and just review how we set this up. So we know the potential due to a point charge is kq over r. And so we have to consider a small element of charge. And then, we think of, for a continuous charge distribution, we break it up into pieces. And in this case, it was particularly easy because we can define this ring with a radius r. And again, every point, because the point is on the z-axis, we have this nice symmetry. And every point on this ring is the same distance to P. So in general, integrating over an area like a disk, that would involve a double integral. But in this case, that's not really necessary. So we can just talk about the potential due to this ring at a radius r at this point P, just because every point in that ring is the same distance away. So we can take the total amount of charge in that ring and then treat that as like, the potential due to that ring. That's dV, that's Ke dq over r, where r is the distance from the ring to the point. And then just, we integrate over the radius from 0 to the radius of the disk, which I'm calling A. And so that gets us, the hard part's done. Setting up the integral is the hard part. Now doing it's going to be trivial, especially because we have an r squared here and an r dr. We can make a simple u substitution. So let's say u equals r squared plus z squared, then du is 2r dr. So r dr is du over 2. I think I forgot a 2 over here anyways. Yeah, there's a sigma over 2 epsilon naught. So yeah, 2 pi ke, that's 2 pi over 4 pi. There should have been a 2 in the bottom, which I forgot to write out. But now let's turn that into a 4. Because r dr is 1/2 du, we can take that 1/2 out of the integral. And then we have du. And then on the bottom, we have u to the minus 1/2. Or here we have u to the minus 1/2. So u is r squared plus z squared to the minus 1/2. The minus brings it down in the denominator. The 1/2 is the square root. And now let's just plug in the limits. If r equals 0, then, so if r is 0, then u is z squared. And then if r equals a, then we have a squared plus z squared for our upper limit. So now let's just do the integral. We have sigma over 4 epsilon naught. The integral of u to the minus 1/2 is 2 u to the 1/2. So, easy to check. 2 u to the 1/2, if you take the derivative of u to the 1/2 is 1/2 u to the minus 1/2. So the 1/2 cancels out the 2. And then we get u to the minus 1/2. So, then we just plug in the limits. Now this 2 and the 4, they partially cancel out. So we have the square root of a squared plus z squared minus, I'm going to leave it as the square root of z squared just because of, symmetry kind of. We could just write that as z because z is a positive number. But, I prefer to leave it this way. And so that's it. And then of course if we were given the radius of the disk and this point z, and the density, we could actually calculate the potential, at any point z along the axis. So again, we'll practice this more during our live classes, just looking at different kind of charge configurations and how to calculate the potential due to that charge configuration. But just taking this idea and considering a little element of charge and then integrating over the entire distribution. So now I want to come back down to this equation and do a problem. But this is one I don't want to make up. I think I have a problem in my notes somewhere that'll work out better than if I just made up numbers. So I'm going to see if I can find a good problem here. Sure, I should have. No, I'm going to make up a problem. Okay. So, erase this. So we've got like 0. Now what I'm drawing, these are called equipotential lines. So equipotential, short for equal potential. And so basically what that means is every point, when you have an equipotential region, that just means that every point in that region is at the same potential. So like on this line, everything is at 0 volts. Here everything is 10, here's 20, 30, and 40. And let's say we have a positive charge. Now the tricky part is going to be making up numbers that's going to give us, a reasonable result. So we're going to launch this particle into this region with an electric field, or into this region with this electric potential, and kind of see what happens. And so I just have to make up numbers that are going to give us something reasonable. So let's say a charge is 12 microcoulombs. So let's see. And I have to give this object a mass. Let's say it's 45 grams. So I want to make up a problem, but let me do something real quick to get some numbers that are going to be reasonable. I'm going to write this down. 1 second. Yeah, I think I want to make this mass a little bit smaller. Let's say 45 milligrams. So it's a very small particle. And in that case, yeah, I'm not liking these numbers too much, but yeah, I just want to have something reasonable here. Let's go with this and see what happens. So the question is, let's say we fire this projectile. It's moving at 5 meters per second. These are kind of ridiculous numbers, but you know, the idea is going to work out. So it has this charge, 12 microcoulombs, and a mass of 45 milligrams. And let's say this particle, once it enters this region with this potential, it's going to slow down. So when there's a potential, it's going to move through this region to some extent. And so there's going to be a change in electric potential, delta V, which means there's going to be a change in potential energy. And so we're going to say that this particle is going to stop at some point. So yeah, that's the idea. The particle is going to stop. So, and we want to find out like how far it's going to go before it stops. And so let's get to the idea. I thought I had this on my notes so I could just look it up. But I don't. But let's say it starts out at point A, and it's going to end up at point B. We don't know where point B is, but supposedly it's going to stop there if I made these numbers work out, right? So I'm just going to put point B at some random place. Here. And because, you know, the reason this potential region exists is because there's an electric field in this region, and we know that electric fields are conservative. And so energy is conserved. We're not considering any other forces acting on this particle. And so we can write down conservation of energy and say energy at A is equal to the energy at point B. It's a conservative field, so that's valid. And we're talking about mechanical energy here, where at point A we have kinetic energy plus whatever the potential energy at point A is, and we're saying it stops at point B, wherever point B is, so the kinetic energy is 0 there. So we just have potential energy at point B. And if we subtract UA from both sides, 1F mv naught squared is going to be UB minus UA. And that's where this formula comes in. We have delta U here. So this would be Q times VB minus VA. Now, one thing we have to be a little careful here is the notation. Because here we have a lowercase v for velocity, and this potential is an uppercase v. So I just, it's hard to tell from handwriting the difference between a lowercase and uppercase. So I'm trying to write these uppercase v's with these tails to make them distinctive. And again, this 0, that's not there. Okay. Now VB minus VA, that's a change in potential. So VA is actually 0, so we can simplify this and say that 1/2 m V naught squared is just Q VB. And then solve for VB. Now, again, I'm not thrilled. I wanted this particle to be moving a lot faster. But let's just see what we get with these kind of ridiculous numbers that I just made up. So I'm going to have to clear some room on the board. Let's actually, let's just kind of review this. Energy at A equals energy at B. It entered with a certain kinetic energy, 1/2 mv squared, plus UA. And that equals UB, plus the kinetic at B, which is 0. And so basically, that's, at this point, we subtracted UA, so we have UB minus UA is equal to that kinetic energy. And that's where we use this equation. So with that out of the way, let's solve for VB, and then I'm going to kind of erase the board, or at least some of it. This would be mv naught squared over 2q. So the formula part's great, it's just the numbers. It's kind of a very tiny particle. It's not moving all that fast. So it doesn't seem like the most realistic problem. But let's plug it in. So our mass is 45 milligrams. So I'm going to raise 45 grams over 10 to the third. Remember, mill is 10 to the minus 3. And let's immediately throw in this conversion factor. A kilogram is 10 to the third grams. So this is 45 times 10 to the minus 6 kilograms. Now we've got V naught squared, that's 25 meters squared per second squared. 2Q, that'd be 24 microcoulombs. So I'm going to write that 24 coulombs times 10 to the 6. Micro, 10 to the minus 6, but it's on the bottom, so we have 10 to the 6. So we're going to get some cancellation, that's a good sign. You have to erase a little more of our picture. Actually, I don't want to erase it. Let's just keep it here. Let's see what we've got so far. Let's clean this up a little bit. Numerically, we have 45 times 25 divided by 24. So we have 47, roughly. And the units, the grams cancel here. We have kilogram meter squared per second squared. That would be a joule. And then over a coulomb. And remember, a joule is a coulomb volt. So a joule over a coulomb is a volt. So we're getting roughly 47 volts for the potential at B. So actually, I should have extended this picture. So here we have point A, where we're moving with this initial velocity, and point B would be somewhere over here at 47 volts. So kind of right at the end of the board. There should be equally spaced lines, so yeah, made it a little past the drawing part, but still kind of reasonable with the picture that we had. So yes, when you have electrostatic fields, you can always use conservation of energy, and so this equation is extremely useful. And I think we'll kind of stop here for this video. And the next one is, we're not done with this topic of electric potential yet. I'm going to have another video talking about, there's a connection between the electric potential and the electric field that we're going to explore in some detail, so that'll be a separate video. So that'll be it for this one.